All right, let's dive right into one of the coolest ideas in chemistry, hybrid orbitals. We're going to uncover the secret shapes that literally define the world around us. And it all starts with a super simple question about a molecule you see, well, every single day.
So why is water, H2O, bent? That classic V shape. It seems like a simple enough question, right? But to really get the answer, we have to first look at what our most basic theories predict. And honestly, that's where things get really interesting.
Okay, so let's set the stage for this molecular mystery. The whole problem kicks off when we put a simple, straightforward prediction from our chemistry textbooks right up against what we can actually measure in a real lab. And they do not match.
Now, if you look at a single oxygen atom all by itself, its electron setup shows it has two unpaired electrons just itching to form a bond. These electrons live in two separate p orbitals, and those orbitals are naturally set up at a perfect right angle to each other. So the simple theory says, well, two hydrogens should just come in and bond right along those 90-degree lines.
If that were true, the angle between the two hydrogens in a water molecule would be exactly 90 degrees. It's a clean, logical prediction. The only problem, it's totally, completely wrong.
Yeah. When we actually go and measure a real water molecule, the hard data tells a very, very different story about its shape. The actual measured bond angle in water is 104.5 degrees. Now that's not just a little rounding error, that is a huge difference, and it's a massive clue that our simple model is missing something really, really important. So this gap between a 90-degree prediction and a 104.5-degree reality, it basically screams that we need a better model. We need a new idea to explain how atoms really arrange themselves when they hook up to form molecules.
And that brings us to the hero of our story, hybridization. This is the absolutely elegant idea that solves our molecular mystery and gives us an incredibly powerful tool for predicting the shapes of all sorts of molecules.
So what even is hybridization? You know what? Think of it like mixing paint. You take a spherical yellow s orbital and a few dumbbell-shaped blue p orbitals, and you kind of throw them in a mathematical blender. What comes out isn't yellow or blue anymore. What you get is a brand new set of identical green hybrid orbitals. Now there are a few ground rules for this whole process. You can see them listed here. A really important one is that the number of orbitals is always conserved. If you put 4 in, you get 4 out. But the most critical rule, the one you really need to remember, is the last one. The molecule's overall geometry actually tells us what kind of hybridization we need to use. The shape comes first, and the hybridization explains. Okay, so let's actually see how this idea helps us build the common molecular shapes we see all the time. We're going to look at the 3 most common types of hybridization. First up, we have sp hybridization. We mix one s orbital and one p orbital. And what do we get? We get 2 brand new sp hybrid orbitals, and they point in exact opposite directions, creating a perfectly straight, linear shape with a 180-degree angle. A textbook example of this is beryllium dichloride. That beryllium atom smack in the middle is sp hybridized, which lets it form 2 bonds in a perfectly straight line, one on each side, with those 2 chlorine atoms. So what happens if we mix one s orbital with 2 p orbitals? Well, we get 3 sp2 hybrid orbitals, and these 3 new orbitals will spread out as far apart as they can get in a flat plane, creating this trigonal planar shape with perfect 120-degree angles between them. The borane molecule, BH3, is a fantastic illustration of this. The boron atom in the center is sp2 hybridized, and it forms 3 bonds to hydrogen that give it that beautiful, flat, triangular shape. And now for the big one, sp3 hybridization. This is what you get when you mix one s orbital with all 3 p orbitals. This mashup creates a set of 4 identical sp3 hybrid orbitals that point to the 4 corners of a tetrahedron, giving you an ideal bond angle of 109.5 degrees. And this is where it all clicks. This brings us right back to our original mystery. The oxygen in water is sp3 hybridized. 2 of those hybrid orbitals form bonds with hydrogen atoms, but the other 2 are holding lone pairs of electrons. And those lone pairs are a little greedy for space. They push the bonding pairs a little closer together, squeezing that ideal 109.5-degree angle down to the 104.5 degrees we actually see. And just like that, mystery solved. So, that's the theory. But how can you figure out the hybridization for any atom in any molecule? It's actually way easier than it sounds. You just need this simple toolkit. All right, here's your cheat sheet. The key is that first column, Regions of electron density. Don't let the fancy name fool you. A region is just a lone pair of electrons, a single bond, a double bond, or a triple bond. The trick is they each count as just one region. So if you have 2 regions, it's sp. 3 regions, sp squared. 4 regions means sp3. See? It's a direct link between the geometry and the hybridization.
So here's your 3-step guide. Step 1. Draw the Lewis structure for your molecule. Step 2. Look at the central atom and just count those regions of electron density around it. And step 3. Match that number to the chart we just looked at. And that's it. You've figured out the hybridization.
But before we wrap up, there's one last really crucial thing we need to talk about. Hybridization is an incredibly powerful model, but we have to remember that it is just that, a model. It's not a perfect snapshot of physical reality.
Just look at this comparison. For water, the 104.5-degree angle clearly points to sp3 hybridization. But now look at hydrogen sulfide, H2S. Sulfur is in the same column as oxygen, just 1 row down. Its bond angle is 92.1 degrees. That's super close to the 90 degrees our original simple model predicted. For bigger atoms like sulfur, it turns out hybridization just isn't as necessary to explain the shape we see.
And that brings us to this really key idea. Hybridization isn't some law of nature that every atom has to follow. It's a tool, a concept that chemists invented to help explain the molecular shapes they were observing in experiments. We basically pull it out of the toolbox when we need it to make sense of the data.
So this leaves us with a final thought to chew on. If our best scientific models aren't the truth, but are instead just powerful, evolving tools that help us make sense of what we observe, what does that really tell us about the nature of knowledge itself, and about how we come to understand the world around us? It's a pretty big idea. Thanks so much for joining me for this explainer.